last lecture that we had. We also studied about Faraday's law, okay, and from there we can see that there is the term which is called induced EMF. So whenever we basically have a changing field, we do have an EMF induced, and that is induced EMF. The same time, if there is an induced EMF, definitely there is going to be some induced current as well. Okay, based on that, we have discussed a few problems, and the direction of induced EMF is also important. You have to identify the direction. So if you consider an inductor, okay, so let's take the heading of the topic as inductance and inductor. Inductance and inductor. Okay, that's our heading for now, this topic. So whatever we are going to talk about is about inductors now, and there is something which is actually called self-inductance. Self. So if we actually have a changing field, there will definitely be some inductance which will be there. Okay, induced current, induced EMF, and so on. But that might happen to a neighboring coil, which is actually called mutual inductance, or it can happen to the coil itself. Let's take an example. Suppose I've got a current I flowing through an inductor. So an inductor would be something like this, turns of coil, right? So this current, if it is variable, okay, it's basically variable or changing. We can say it's a variable or it's changing. So if the current is keeping on changing, there will be an induced EMF and an induced current that will be there. And let's say uh, this current is increasing or decreasing. Variable means it will either increase or it will decrease. Okay, for that we are going to have a self-induced current in the circuit. Induced current. Okay. So what happens is, if I just take one example, let's say for example I am having a current, and this is my inductor, and this is my I, and this current that we have is increasing. The question is, what will be the direction of the induced current? Okay, the answer is simple, because from Lenz's law we know whatever is the cause producing the induced EMF or the induced current will try to oppose it. So this is the current that was originally there, because of which you have your induced EMF or current, and that is increasing. So this induced current that we have in the inductor will try to reduce it. So that's why the direction would be in this direction. Okay, so this induced current is in opposite direction, opposes. This is important when we are talking about directions. Okay, that's where actually study. Now what about current decreasing? So maybe the current is flowing in this direction, same thing, but this time this current that we are having is decreasing. Now if this is decreasing, then the induced EMF or the induced current will try to increase it. So this is flowing in this direction, it won't oppose it, it will try to increase the value. Okay. So that's how we actually are going to find out what is the direction of current. Okay, and this is nothing but a consequence of Lenz's law. So that is important. So what do we conclude here? That if I increases, this is very much connected to our last class, increases, the magnetic field will definitely increase, and if the magnetic field increases, the flux will increase. Because of the magnetic field, flux is B dot A, flux is B dot A, that is also going to increase. Okay, and because of this increase in flux, or we can say changing flux, you are going to get an induced EMF. right? This is an entire story here. And because of that induced EMF, you are going to get an induced current. And that is very important when we are actually going to study this, okay? And because of this Lenz's law, this induced current, let me write it down as II, opposes I, right? So this is my induced current II, and this is my current I. So this will try to oppose it, okay? So what happens is, if you want to find out the direction of the induced current, we can do a lot of things here, okay? Everything is connected here. Let's say I have got a magnetic field which is coming out of the plane of the board, like this is my magnetic field, and you have a coil here. It's a current carrying coil, okay? Now if you use your thumb rule, okay, the magnetic field is in the downward direction, okay? Just a second. So the magnetic field is in the upward direction, and if you just use your thumb, okay, and try to find out the direction of the current, okay, you can find it. So if you use our thumb upwards, okay, you can check it on your screen as well. It's not going downwards, it's coming upwards. So the current will be in this direction, right? And let's say this magnetic field is increasing. So if this magnetic field is increasing, the current is also increasing, okay? And if we think about the induced current, it has to be in the opposite direction. It has to be in the opposite direction. So this is my I, and this is my induced current. Now, if the induced current is in the opposite direction, because of the induced current, again you will get a magnetic field, and that magnetic field will be going in the downward direction. This is coming upwards, increasing. This will go in the downwards direction, decreasing, trying to reduce. Okay. Okay. So that is what happens in induction and induced current. Okay. So this was the basic idea, kind of revision with more examples. Now let's basically consider self inductance, the idea of self inductance. There should be some relation that we should have, mathematical relation, which we are going to use later also for numerical problems. Those things will be helpful. So if you talk about self inductance, what it means is that you are basically having this current carrying loop, as I said. Let's say this is one loop, two loop, three loop, four loops, and so on. N number of loops are there, okay? And let's say this is my one loop. This is my one loop, okay? And there are total n turns, okay? So you will basically have a flux, okay, a flux because of this one loop. So I can say this is magnetic flux linked with just one coil, not n coils, one coil, one turn of coil, okay? So if I want to find out the total flux, let's say phi t, this is nothing but my total flux. That would be obviously the flux because of one coil into the total number of turns or total number of coils. So 1, 2, 3, 4, and so on. So N5 would be giving you the total flux. Okay. At the same time, we know it was, obviously experimentally also observed that this total flux that we are talking about is directly proportional to the current. That means more the current here, more would be the flux. That's quite obvious, right? More current, more would be the magnetic field generated, and more is stronger the magnetic field, will have more lines of force. As a result, will be more flux, right? So phi t is directly proportional to the current, or we can say phi t is equal to. We have to introduce a constant. That constant conventionally is written as L, okay, and this L is actually called coefficient of self inductance. Coefficient of self inductance. Okay, this is a constant for a particular system of coil. Okay, and this is something which is helpful to understand self-inductance better. So uh, what was my phi total? Phi total was n phi, so I can simply write it down as n phi is equal to L into I. So I'll write it down as L into I. And from this, I can find out what is my coefficient of self-inductance for a particular circuit. L is equal to N phi divided by I. Okay. So this is my coefficient of self-inductance. If we are having a self-inductance of a coil, we should know what is the coefficient of self-inductance. Okay. At one look, it might seem that coefficient of self-inductance cannot be a constant. The answer is wrong. It has to be constant because phi is the flux, I is the current. It seems as if it is inversely proportional to the current, directly proportional to the flux. But we have to understand one thing, that if the current increases, flux also increases. Current decreases, flux also decreases. So this ratio will always remain the same. As a result, this will remain the same, right? So if you just look into the unit of L, check the unit. You see, this is L, this is N number of turns, no unit. Phi is nothing but Weber flux, right? Remember, Weber by length. Oh, sorry, current, ampere, right? Ampere. So Weber per ampere. Okay, it's also called Henry. So magnetic field unit is Tesla. Flux unit is Tesla meter square, which is nothing but Weber. Self inductance is Weber per ampere. That means Henry. Okay, so these units do confuse us, but we have to remember those units. They're very important. And what does this L depend on? Okay, this L does not depend on the current and all, because that is something which is already there. So this L depends on the size and shape of the coil. Okay, just like a resistor we know, similarly this also, size and shape of coil, it is the factor on which it depends. Okay, so we can actually get the induced EMF now, because we already know what is the relation for induced EMF. So if you remember, induced EMF we usually denote it by E is equal to minus, because of the Lenz's law, divided into d phi total divided by dt. So you can simply do it. So minus d phi total is L into I. So let me write it down as L into I. This relation is very handy, most important. We are going to, if you solve numerical problem based on this topic, you have to use this. So we can say E is equal to minus L di by dt. This is my relation for induced EMF. Okay, so induced EMF plays a very important role when we are talking about inductors. Okay, so if we basically consider a solenoid, we can also find out what is the self inductance for a solenoid. Okay, it's a very short derivation. Let's do it quickly. So L, that means coefficient of self inductance for a long solenoid. Okay, so if you're basically considering a long solenoid, let's say this is my current, and you are having a solenoid here, and let's say the length of the solenoid is L. Okay, and this obviously will have some radius. So this solenoid is having radius this. So as I told before, if you have a solenoid, you basically take a paper core and roll that wire on top of that. Okay, so that's the radius, and N is the number of turns. Okay, certain things are important. We have used those before also. Wasn's notation, you should not get confused. Capital N is number of turns per unit length. So the total number of turn would be nothing but n into L. Okay. So small n, capital N, there is the difference, which is important to remember. Okay. Also, we have derived it, the magnetic field due to a solenoid. We can use Ampere circuital law and find it out. We already done it in the last class. B was equal to mu naught N I. What I want to find out is L. Okay. What I want to find out is L. So if we talk about the flux with each coil, phi with each coil. Okay, so that is nothing but B dot A, but that is BA cos theta, right? So this is BA cos theta, but theta is 0 degree here. Why it is 0 degree? Because this is the coil, this is the direction of the area, this is the direction of the magnetic field as well. So that would be 0 degree, okay? Because it's a three-dimensional picture, so you have to imagine that. The cos 0 is 1, so you can simply write it down as B into A. Okay, that is phi flux with each coil. So that means I can write down phi as B is mu naught Ni. So I'll write it down as mu naught Ni. The radius of the coil is given to be R, so the area would be pi R square. Please remember this is with each coil, not the total. Okay, we are talking about each coil. So that means from here I can find out what is my total flux, right? So if I find out what is my total flux, so total flux phi t is equal to, you know, we have already seen that you have to take how many turns are there, n, and flux for each turn is phi, so we can write it down as n into phi. So what is n? N was, if you check here, capital N is nothing but small n into L. Capital N is equal to small n into L. Okay, so that means I can write it down as small n into L into phi. Phi we have just now found out. This is nothing but mu naught Ni pi r square. So you can square out the n here. So you can simply write it down as mu naught n square pi r square into L I. So if you look on top, our topic was find out L for the solenoid, right? So we have to find out L. But we already know what was my total flux. My total flux was L into I. So I can replace it here, right? So I can write down L into I is equal to mu naught n square pi r square L I. Let's cancel this I. We have got the coefficient of self-inductance for a solenoid. It depends on permeability of free space, which is a constant. It depends on what is the turn ratio, number of turns per unit length, square of that. It depends on the radius of the coil, and of course it depends on the length of the coil. We can write it down in a different form as well. We can take this n square as n square by L square. So I can write it down as mu naught n square by uh, L square into pi r square into L. So that cancel, I'll have this relation. So it depends on what are the parameters that are being provided in the question, and based on that you can actually use this formula. But many a times, how to derive this formula is also important. This can be considered to be a normal numerical problem. You can have different variations in the coil and think accordingly. You can think it for a toroid also. Okay, if you think about a solenoid, it is nothing but a straight coil, and a toroid is something like this. You basically have a circular core. Okay, you basically have a circular core, and you have the coils around this circular core. So it is something like this. So complicated questions might be from this. This is basically a toroid. So here also we can use the same logic, but then you want to find out the total length, then you have to make it straight. What is the radius of that toroid, take the circumference, and then use the relation.